I have something mind-blowing for you. Let's consider the plane R2. Okay, R2 is just the standard plane, R squared, okay, the Euclidean plane. Now what we're going to do is we're going to delete from R2 Q2. Okay, so Q2 is going to be the square of the rational numbers. It's all pairs of points A comma B, where A and B are both rational numbers. Okay, this is Q2. And what we're going to do is we're going to delete Q2 from R2. Okay, so Q2 is like a minefield in the plane R2. Okay, there are just so many rational numbers. I'm just going to be deleting things everywhere. Okay, just lots and lots of dots. I can't even begin to explain how many dots we're going to delete. But we're going to consider this space. Okay, it's a space, whatever that means. We're going to prove it is path connected, which means that any 2 points in R2 minus Q2 can be connected by some path that completely avoids all these mines, all these points where the coordinates are both rational numbers. Okay, and this is quite crazy, but it's so cool and beautiful, and anyone can understand this proof. It's an introduction to topology. We're going to prove this statement. So let's just dive right into it and get into the proof. Now, first of all, note that, of course, R2 itself is path connected. If I just draw the plane, then it's going to be path connected. So we have R2. It's path connected. For example, if I take 2 points, and I'm going to be suggestive here, I'm going to take pi comma pi, and I'm going to take 2 pi comma 2 pi. Okay, 2 points. Now, of course, there's always, it doesn't matter what they are, there's always a straight line path that connects them in R2. Okay, just a straight line path. Now, here's the issue. The issue is that in R2 minus Q2, right, both these points are in R2 minus Q2. Because to be in Q2, both their coordinates have to be rational. Pi and 2 pi comma 2 pi, neither coordinate is rational. So it's in R2 minus Q2. But if we try to draw that straight line path in R2 minus Q2, it won't be in R2 minus Q2. Because in between, for example, pi is roughly 3.14 something, 2 pi is going to be 6.28 something. But in between, for example, if we take something like 4.5 comma 4.5, that's going to be on the line y equals x. And that's not going to be in R2 minus Q2 because it is in Q2. So it is a mine that we're trying to avoid, where Q2 is like the minefield. So how are we going to connect these 2 points in R2 minus Q2? Well, I'm going to give you a mathematical proof that any 2 points can be connected, but how would we handle it in this situation? Well, we do the following trick. Instead of going like that diagonally, we would first go from 2 pi comma 2 pi all the way to pi comma 2 pi. Okay, now this is fine because as long as we are staying on this horizontal line, right, the y coordinate is going to be 2 pi. So therefore, it's never going, no point on this horizontal line is ever going to touch Q2 because one coordinate is always going to be irrational, the y coordinate being 2 pi. Similarly, if we then went along this line, we would avoid anything in Q2 because, again, the x coordinate on this line is always pi. So I could even draw this. Y coordinate is 2 pi on the first line, x coordinate is pi on the second line. So therefore, one coordinate is irrational, which is all we need to avoid Q2. So this path would work, okay? Even though you can't see, there is so many mines here, you can't see them, I haven't drawn all of them, but you avoided it by this path. So in this sense, you can connect these two by a path, but now let's rigorously prove, and this is such a fun exercise, we're rigorously going to prove this is path connected. Okay, so here's the proof, and it's quite an elegant argument, and it's going to be slightly subtle because this is not the general case, so we have to be careful. So here's what I'm going to prove, okay? So step 1 of my proof is I'm going to argue all we need to do is connect any point in R2 minus Q2 to some fixed one. Okay, let's say pi comma pi. Why? Because if I can connect any point within R2 minus Q2, okay, within the space R2 minus Q2, as long as I can connect any point to pi comma pi, then I can always connect any 2 points in R2 minus Q2. Because if I have another point in R2 minus Q2, I first connect it to pi comma pi, then I connect it to any other point I like. So this is like the home station. I go through my home station and go anywhere I like. Okay, so that's all good. So all I have to prove is that anything in R2 minus Q2 can be connected to pi comma pi. So let's fix a point in R2 minus Q2. Okay, let's fix a comma b inside R2 minus Q2. What does it mean to be inside R2 minus Q2? This is something we have to get our head around. It just means that at least one coordinate is irrational. Okay, both coordinates are rational is in Q2. The the opposite of that is to say at least one coordinate is going to be irrational. So let's consider cases. Okay, we're going to consider cases, and actually I'm going to do it in two cases, and I'm going to ask you to fill in the other case. All right, so we have a comma b in R2 minus Q2. How are we going to connect it to pi comma pi? Okay, so we know that at least one of the coordinates is going to be a irrational number. Let's assume this is case 1. Okay, so I'm going to say case 1 is that A is irrational. Okay, so either A or B is irrational. We don't know which one, but we know at least one is. So let's consider the case where A is irrational. How are we going to connect A comma B to pi comma pi? Well, here's what we're going to do. We know A is irrational. It's the x coordinate, so we have our A comma B. Now, because A is irrational, we don't know, B may be rational, okay, could be, and that would be a fine point in R2 minus Q2. However, if we change the B, okay, B is the y coordinate, if we change the B by going on a vertical line, our x coordinate is always going to be A. So our x coordinate is always going to be irrational, and our vertical line is going to be inside R2 minus Q2. Okay, so we are allowed to move freely on the vertical line. This is crucial because what we can do is we can move freely on that vertical line to connect to pi comma pi. But we have to do it in two steps like in the first example I gave. So the first thing is we can adjust our b so that b is equal to pi. So we can connect a comma b to a comma pi. Now pi may be less than b, pi may be greater than b, we don't know which one, but regardless we either go up or down, we fix a, so it's always in R2 minus Q2 because a is irrational, and we connect it to a comma pi. That's fine. And now once we've connected to a comma pi, we can now pivot with the pi. We now can allow our a to vary, our pi is irrational, we allow our a to vary, and our a can now be connected to pi along a horizontal line. Okay, so it doesn't matter if a is less than pi or a is greater than pi. Okay, so if a is greater than pi, we're going to go to the left, otherwise we'd go to the right, and we'd eventually connect to pi comma pi. Okay, now this composition of these two lines, this vertical line and this horizontal line, is living entirely in R2 minus Q2. Now you might want to know, what is a rigorous mathematical proof? What's my path? How do I write it down rigorously? And I want to show that to you because I don't just want to show you math, I want to teach you math. So this is very important mathematical rigor to complete the argument. That's the intuition. How are we going to do it? So we're going to define a function in two steps. Okay, so our function is going to be f of t is going to equal to the following. It's going to equal to a bt, b times 1 minus t plus pi times t. Okay, it's going to equal to that. Now why have I chosen this? Well, notice that f of 0 at time t equals 0, we're going to get b plus pi times 0. We're just going to get a comma b, okay, at time t equals 0. Then at time t equals 1, when t is 1, f of 1 is going to be, well, b times 0 and pi times 1. So it's going to become a comma pi. So this is the path that successfully connects a comma b to a comma pi. Very rigorous. And then we define g of t to equal to, so again we define g of t to be the following, a times 2 minus t plus pi times t minus 1 comma pi. Okay, now observe the following. At time t equals 1, g of t is going to be a comma pi. So it's going to be here. At time t equals 2, g of t is going to be pi comma pi. So it's going to be here. So if we compose f of t and g of t on the interval 0 comma 2, at time t equals 0 we're going to be at a comma b, at time t equals 1 we're going to be at a comma pi, and at time t equals 2 we're going to be at pi comma pi. And at no stage is our path going to touch Q2, because as long as t is between 0 and 1, our a is irrational, so one coordinate is irrational, and as long as t is between 1 and 2, our second coordinate is going to be irrational. So this is the rigorous proof that this path, which we can define as follows, piecewise, so I'm going to actually write it down. We can define our path piecewise, so h of t is going to equal to f of t when 0 less than or equal to t less than or equal to 1, and g of t when 1 less than or equal to t less than or equal to 2. Okay, now h of t is a continuous function because it's two continuous functions glued together and there's no discontinuity at the gluing point. Continuity of course matters because otherwise you can just jump around freely and we can connect any two things by a discontinuous path. So we have to ensure continuity, but f of 1, as we've checked already, is going to be a comma pi, and so is g of 1. So that's our continuous function that connects a comma b to pi comma pi. And then I want you to sort of explain, drop a comment down below, how would we then write our continuous function to connect a comma b to c comma d for any pair a comma b and c comma d in R2 minus Q2. Okay, and I've sort of avoided having to deal with too many cases. The case where b is irrational is also the same. If you want practice, try to write that down. It really helps a lot to master mathematical reasoning. Try to write down a proof when b is irrational, how we'd connect a comma b to pi comma pi. And check out this video. It's going to pop up on the screen. It's more topology for you. I've shown you how to understand path connectedness here. It's a topological concept, points at topology. In this video, I introduced the idea of compactness. Not connectedness, but compactness, all from scratch. What are open sets? What is compactness? Beginner topology for everyone, and prove the closed interval is compact in just 15 minutes. It's a lot of fundamental ideas all in one video. You're going to love it. Please check it out here. And if you want a lot more fun math content, check out my video here. It's a proof that any increasing function has to be continuous almost everywhere. Another fun proof, which actually involves the rational numbers secretly, but it's a real analysis proof. You're going to love that. More math proofs. I hope you have an amazing day. Thanks so much to Alex and Nathan for their support on Patreon.